Welcome to This Explainer. Today, we're stepping into what I like to call the medical courtroom. We're going to conduct an absolute audit of the evidence, pulling apart statistical math from clinical reality. Look, if you've ever stared at a clinical trial and just felt totally overwhelmed by a wall of data, well, you're in exactly the right place. We are going to break down how to truly judge medical evidence using some really clear, structured concepts. Okay, let's just dive right into this with a classic 50-50 dilemma. Imagine a clinical lawyer slamming this piece of data onto the judge's desk. Your Honor, a massive study shows this new drug lowers systolic blood pressure by 0.5 millimeters of mercury. And the p-value? It's a tiny 0.001. The lawyer immediately declares a medical miracle, demanding me halt the trial because, obviously, the drug is just that good, right? But wait, is it actually a breakthrough? As the judge in this scenario, you need to know exactly how to evaluate this claim. To answer that, we really have to explicitly separate two concepts that get confused literally all the time. First, we have statistical significance. This is purely a mathematical flag. It just tells us if an effect is mathematically real and not just some fluke in the data. But on the other side, that is clinical relevance. This is the actual, real-world magnitude of the benefit to the patient. A blood pressure drop of 0.5 might be mathematically real, but let's be honest, it's practically meaningless for a patient's actual health outcomes. A mathematically real result absolutely doesn't always translate to meaningful patient care. So here is the docket for today's audit. Number 1, the significance versus relevance audit. 2, p-value mechanics explained. 3, confidence intervals and precision boundaries. 4, the interlock drill, where we'll sight read data. And finally, number 5, our executional pearl on overlapping CIs. Let's get into it. Section 1, the significance versus relevance audit. Mathematical probability versus clinical reality. Before we can even begin to look at the clinical impact, whether that drug actually saves lives, we first have to determine if the data represents a true signal or if it's just random noise. In statistics, our entire goal is to filter out the noise of random chance to see if there's a real mathematical signal hiding underneath. If it's just noise, we throw the case out. If it is a signal, well, then we proceed to ask if it actually matters clinically.
Moving to Section 2, p-value mechanics explained, putting the p-value on the stand.
All right, it's time to call the p-value to the witness stand. This is arguably the single most misunderstood metric in all of science. So let's audit what this number actually means. Here is the strict mathematical definition. The p-value is the probability of obtaining a result at least as extreme as the one observed, assuming the null hypothesis is completely true. The null hypothesis, remember, is the baseline assumption that the drug does absolutely nothing. The p-value tests the strength of the evidence against that assumption. What it does not do, under any circumstances, is measure the magnitude or the clinical importance of the effect. So, how do we actually use it? Well, we map out a threshold. A small p-value, typically less than 0.05, flags that the observed data is highly unlikely if the null hypothesis were true. It's signaling a statistically significant difference. On the flip side, a large p-value, meaning 0.05 or greater, points to random chance. It tells us the data is perfectly consistent with just background noise. Now take a look at this quote. You will hear incredibly smart people say exactly this. Well, since p equals 0.03, there's a 97% chance this drug works. I want you to recognize this right now as a fundamentally flawed piece of evidence submitted by the defense. We have got to slam down the gavel on this. This is what we call a dumb mistake. The p-value is calculated by assuming the drug does not work. It simply means there is a 3% chance of seeing this big of a difference purely by luck if the null hypothesis were actually true. It tells you the probability of the data given the null hypothesis, not the probability that the drug works. Seriously, lock that into your memory right now. Section 3, confidence intervals, precision boundaries, shifting to a range of precision. With the p-value stepping down, I want to call our star witness to the stand, the confidence interval. We're shifting our focus here from a single rigid point estimate to a much more informative range of precision. A confidence interval gives us exactly that, an estimated range of values. Think of the classic 95% confidence interval like this. If you were to repeat the exact same experiment 100 times, 95 of those calculated intervals would contain the true population mean. It gives us this beautiful visual boundary of where the real answer most likely lives. The secret to reading this is what I call the width factor. The width is a direct indicator of precision. A narrow CI, that means high precision, which is usually driven by a massive sample size or very low variance. But a wide CI, that means low precision, indicating the study was small or the data was highly scattered.
And here is another piece of faulty logic that frequently trips up even the most focused learners. You'll see a wide interval, and someone will confidently claim, well, the confidence interval is really wide, so the study's data must be wrong.
Time to debunk this second dumb mistake. A wide interval does not mean the data is incorrect. It simply means your precision is low. You're dealing with a small study or highly variable data, which leaves you with poor precision regarding the exact size of the effect. The data isn't wrong. It's like a flashlight beam. It's just wide and fuzzy instead of a sharp laser pointer.
Section 4. The interlock drill, sight reading. Reading significance directly from CI boundaries. Now it's time to teach you how to be the judge. This is the interlock drill. I'm going to show you how to read statistical significance purely by sight without ever glancing at a p-value. The absolute crucial point here is knowing your null value. For ratio metrics, things like relative risk, odds ratio, or hazard ratio, the literal tripwire is the number 1.0. A ratio of 1.0 means there is equal risk between the two groups. Basically, the intervention did nothing. If your 95% confidence interval touches or includes 1.0 within its range, bam, it fails the audit.
However, for difference metrics, like absolute risk reduction or mean difference, the absolute boundary line is 0. A difference of 0 means 0 difference between the groups. If your confidence interval includes 0 within its range, again, it fails the audit. It is simply not statistically significant.
Let's build some muscle memory with a rapid-fire drill. Example A, an odds ratio of 0.75, with a CI from 0.52 to 0.98. This is a ratio. The interval stays totally clear of 1.0. Verdict? Significant. Example B, relative risk of 0.60, CI from 0.35 to 1.15. Uh-oh, this one crosses 1.0. Verdict? Not significant. Example C, mean difference of negative 1.2, CI from negative 1.8 to negative 0.6. This is a difference metric, so we look at 0. It stays clear. Verdict? Significant. Do you see how fast that is once you know what to look for?
Let's look at this in the wild on an actual forest plot. Check out that vertical line at 0, that's our null value for a difference metric, which in this case is the reduction of a cough in days. Those black dots, those are the point estimates, and the horizontal lines are the confidence intervals. If a horizontal line crosses that vertical 0 line, it's not statistically significant. But if it stays entirely to the left or right, it is a mathematically real signal. You can literally audit an entire paper in seconds just by looking at the forest plot.
And finally, Section 5, the executional pearl, overlapping CIs, the ultimate inferential logic test. Let's see how this builds into advanced analysis. This is our executional pearl, the ultimate inferential logic test, when you're comparing two independent groups against each other. When you're looking at overlapping confidence intervals between two groups, here are the exact rules. First, if there is no overlap at all between the two intervals, the difference between the groups is always statistically significant. Second, if they overlap slightly, they actually might still be significantly different. You cannot automatically assume they are identical. But here is the ultimate rule. Before you even look at the overlap, always check the null boundary first. If either group's interval contains the null value itself, the intervention is a failure, and the audit stops right there.
We have covered a lot of ground today, from the pure mechanics of the p-value to sight-reading confidence intervals. You now have the exact tools to look at a study, ignore all the hype, and instantly determine if the data is mathematically sound. But I want to leave you with this one final thought. If you can now spot mathematical significance purely by sight, are you ready to be the ultimate judge of clinical reality? Remember, just because a study passes the mathematical audit, it doesn't mean it actually matters to the patient sitting right in front of you. Keep auditing, keep questioning, and I'll see you in the next explainer.